Okay, so we are just picking right back up where we left off, and we had just talked about top-down and bottom-up processing. Now we're going to talk about how we study the perceptual process. So we talked about those 7 steps at the beginning of the course here, and we're going to talk about how we observe these perceptual processes at different stages. And so we've kind of broken it down into 3 relationships, A, B, and C. And the rest, a lot of this course will talk about these different processes in relation to these kinds of relationships. So the first relationship is the stimulus perception relationship. So do you perceive that distal stimulus? Is that something like, I see the thing, okay? The stimulus physiology, or relationship B, is, does your brain recognize that thing? So you may or may not know what you're looking at, but does the brain react to the stimulus? And the relationship C is, does the brain react, and do you actually understand what it is or perceive that you're looking at? So the goal of perceptual research is to really understand each of the steps in the perceptual process that lead from stimulus right in front of you to that behavioral response, the last steps of perception, recognition, and action. So remember, we're still looking at the 7 steps of the process of perception, but now we're breaking it down into relationships that we can actually quantify and study and be able to determine, is there a relationship between these things. So the next thing that you'll see is how these things are sort of broken together. Okay, so we have the relationship of we have A, we have B, and we have C, and then here we have the 7 steps broken down. So if you look at the 3 boxes here, okay, so stimuli is the stimulus is going to be steps 1 and 2, right? Proximal and distal stimulus is steps 1 and 2. Physiology is broken down with the steps 3 for processing and 4 for receptors. And the 3 behavioral responses, which is perception, recognition, and action or behavior, are broken into the behavior category. And so these relationships are going to study the interaction between all of these steps together. And so this is kind of a visual way to break this down. So the first one that we're going to talk about is relationship A, which is the stimulus perception relationship. And that's the main relationship that was really measured during the first about 100 years of perceptual research. So before physiological methods became widely available, like looking at EEG, MRI, and even sort of the even more basic physiological processes and methods, this was something that really drove most of the research. So that stimulus perception relationship, or relationship A. So I've got a few videos on here that demonstrate what I'm going to talk about, and these are really, really interesting. So the first 100 years or so, we used this process of looking at what I'm going to talk about, oblique effect by hand. So the oblique effect, and we're going to get to this more later, has been used when studying the relationships of A and B. But we're going to talk about this here in a minute. This is going to become a little bit more relevant. So one thing that you can do is look at gradients, okay? So I'm going to talk about gradients first, and then I'm going to talk about oblique. So when it comes to gradients, what we're looking at is how far do these bars have to be spaced apart before you realize that there are bars there. So here, notice that the distance between these two, okay, is further than the distance between these two. And to show people different gradients, okay, is to show them different spacings to see, okay, at what point do we do this where you can no longer tell that there is a space between these lines. And eventually you're going to get to a colored in version of your light. I can't tell that there are any lines here. It just looks like a colored circle. Okay? And so by studying the gradients, you're going to be able to understand at what point a person can see or observe or perceive the stimulus, okay? So we call this whole process grading acuity, okay? So at what point do you look at this and determine that the line widths are so close together that you can no longer determine what orientation the circle and lines are going? So here you can very easily tell that these lines are straight up and down. Okay, so this is how we test it. You can tell me, yes, the lines are straight up and down. Now, someone could obviously lie and say, oh, I don't see the lines anymore. So the way that we test it is by using orientation. So if you look at these lines, okay, so these lines are vertical, these lines are horizontal, and these lines are slanted or oblique. Oblique is anything other than vertical or horizontal, okay? And so when it comes to measuring the relationship between do you see the stimulus, okay, we ask people, okay, now what orientation are the lines? You would say here they're vertical, here you would say they're horizontal, and here you would say they're slanted upwards to the right, okay? And what you would do is you would change the distance between these lines and change the orientation and ask the person, well, what orientation are the lines now? And then if they can say, oh, okay, well, I can see them moving to the left or moving to the right or straight up and down or horizontal, then you know that the person can see it. If they see this and you say, what's the orientation? They'll say, I don't know, I can't see it anymore. So at that point between here and here, okay, you're going to say, okay, well, this right here is the least amount of change that requires us to be able to see that there are lines there, okay? Interestingly, and this is the reason why I'm showing a ferret here, a lot of work has been done on ferrets, and we've found that in the case of ferrets, for example, they are able to see a different orientation in terms of what's easier or more difficult. When it comes to humans, studies find that these horizontal and these vertical and horizontal lines result in much better acuity than the oblique effects, okay? And so if we test people, we find that they are much better at determining this acuity in either vertical or horizontal lines. Once you slant the lines and make them oblique, it becomes a lot more difficult for people to be able to determine the orientation and to see the difference. Now, when it comes to ferrets, for example, you can look at the physiological response better in animals because you're able to actually open up the brain of an animal and place electrodes directly on it. So when it comes to measuring physiological response, we're limited in humans because we're really limited to non-invasive measures. We don't want to open a person's brain and put electrodes on it and see what's happening. We can confirm what we think is happening in animals that we think is happening in humans. So in 1998, there was a group that measured the relationship between this bar orientation, right? So this is the stimuli here. So between the bar orientation and brain activity in ferrets. And they found that just like humans, the vertical and horizontal orientations generated greater brain activity than the oblique effect. And it seemed that they were producing a larger physiological response than the oblique orientation. Now, they found that in ferrets. We have evidence through relationship A, which is us asking people, do you see this better, okay, in humans. So therefore, we combine this and say, well, we might see this effect in humans, physiologically speaking, if we see it in animals. So the idea is that you combine relationships A and B by inferring the relationship C, okay, which is that we see the stimulus, we perceive the stimulus, and the brain, the physiological response, is also perceiving it, okay? So that is us combining all three relationships together. There's a stimulus, I see it. So for example, there's a stimulus, here's a tree, okay, and a person here. The stimulus is seen, it is perceived, and the brain also changes in response to seeing it. So that's confirming relationship A, relationship B, and relationship C. When it comes to humans, we can look at something like, for example, fMRI. And here we can actually see sensitivity to different orientations. And here, this study that was done in 2000 actually confirmed in humans relationship C, which is that the human can recognize, okay, the brain, the physiological response is recognized in humans by perception as well. So remember, C is physiological perception. So this woman here says, okay, I see that the lines are slanted. Here I see that they are horizontal. Here I see that they're slanted. She says, I see it. And then also her brain, okay, says, oh, I also see it. So that is confirmed that the action, the stimulus, is perceived as well as changes in the brain. So we've, in this particular study, confirmed again that sensitivity is highest to vertical and horizontal orientations. So here and here produced the strongest effect in the fMRI response. So here you can see the bars going here and here. Okay, that is greater sensitivity than here and here. And so what this is showing us is that, again, we confirm that this relationship C is consistent with relationship A, which is I see this better than this, and relationship B, which is, of course, the physiological response of the brain's reaction here. So, by combining all three relationships, we have now confirmed that this is what we see in the case of vision, and this is what our brain sees, and that all three come together. Now, when we are measuring perception, we use something called absolute threshold, which is the absolute minimum, smallest amount of energy needed to detect that a stimulus is there, okay? So, for example, let's say you're in a room, okay? You're in a bedroom, okay? And it's dark, okay? you would then change the lights to determine how dark does that room have to be to where you can't see anything, right? And we measure this through the method of limits. So we can change intensity. So we have the room slightly lighter, go slightly darker, okay? Or we can go slightly darker and then lighten it up, okay? So we can go ascending or descending order. Think of this also with sound. So let's say I have, I have a radio and I turn the volume up slowly, slowly, slowly. And at what point is it that you can no longer determine that a change has been made? So, for example, have you ever had somebody turn, the TV's like blaring really, really loud, okay? It's going on and you're like, oh my God, turn that down. And then someone says, well, I did turn it down. You did not detect a change. Therefore, the threshold had not been met. If they had turned it down a bunch, then you would have noticed the change, okay? And at the point that you perceive the stimulus is the point that absolute threshold has been met. And then you're going to then measure the crossover point to determine, yes, this is the actual threshold. So here's an example. So this would be using the method of limits. Okay, this is using method of limits to determine the absolute threshold. So if you were, this is the intensity, and let's just say, we're not going to use the actual experiment. Let's just say this is sound. Okay, let's just say that we're using the amount, the intensity of sound, just, for ease. Okay, did you hear it? Yes. Did you hear it? Yes. Did you hear it? Yes. At 100, did you hear it? Yes. At 99, did you hear it? Yes. At 98, did you hear it? I don't hear anything. Okay. Here we can say that's the threshold. Okay. And then we will try it again. Okay. Did you hear it at 101? Yes. Did you hear it at 100? Yes. Did you hear it at 99? I did not. Okay. Ask again. Okay, now at this point, they heard it to 98, but by 97, they didn't hear it. Okay, and continuing on to determine, change, going from high to low, low to high. Did you hear it now? Do you hear it now? Do you hear it now? At these dashed lines, this is the crossover point. At this point, we can say, well, we think that the threshold falls between these values. When you start to get here, it starts to get gray. At 101, everybody recognizes it, and at 97, nobody hears it. So in between these values here is the absolute threshold of the absolute minimum that you need to hear this sound. So that's using the method of limits. And we can do this with sound, we can do this with light and vision. So for example, we can see here, after you maybe, so you come into this situation here, okay, what do you see? What items do you see if you're in this scene, okay? And then you can take a person and put them into a dark environment and then say, we're going to spend 15 minutes here. And then now what do you see? And what you find is that people do adapt to the environment. And so perhaps they're able to actually see more items because there is actual difference that occurs physiologically for the perception or the threshold for perceiving or seeing light. So that's how we measure perception. So I'm going to close the video here and I'm going to pick up on the next one, and you can email me if you have any questions about these examples.